Okay, now let's start with the same example from last lesson. I'll use your school example so that when you hear it again at school, see if it makes sense. Okay. Hopefully you don't get confused further. If you get confused, just forget what the teacher said and just remember what I said, because sometimes I find the teacher's explanation, sometimes it doesn't help us much. We'll see. Okay, skip these ones. All right. Okay, hypothesis testing. You know what hypothesis means?
Educated guess.
Yep, educated guess. Okay, good. Now, the idea is that the idea behind hypothesis testing is that you would have like a running hypothesis. So, for example, in this case, okay, let's just say your the current assumption is that the average, right? The average, let's say, lifespan, right? Average lifespan, okay, is 80 years old. Okay, let's say that's the current hypothesis, aka the null hypothesis, H naught. Yeah, okay, or you can write it as the mean of the, so this is the average lifespan, so that's the mean, yeah, so this is the mean of the main hypothesis, right, or the null hypothesis. I'm using a different notation, so hopefully it makes sense, and I'll change it back to your school notation. So the mean the mean of the hypothesis is 80 years. So you're saying, okay, the lifespan is around 80 years and it's normally distributed. That means the graph has to look something like 80 and then it sort of curves around it like that, right? Okay. Now the question asks, okay, just does it indicate that the average lifespan is greater than 80 years? So they're saying that, okay, so from the data, so I'm going to move that away, right? Is it now over 80 years? So they're saying that, okay, the mean of your what you're trying to prove is the alternative hypothesis is, or you're saying that, okay, the mean of the hypothesis, okay, yeah, the mean is more than 80. All right, so they're saying, okay, is it more than 80? Because if it is more than 80, then the distribution has to somewhat look like that, right? If it's more than 80, then it will kind of look like that, right? It gets shifted to like some sort of value, 80 something. Okay, now if we assume that, so we ignore this one for now. Okay, if we're assuming that the current average lifespan is 80 years, and then let's say you do an experiment. Okay, experiment. When you ask 200 people, okay, you ask 200 people, what you find out, so n equals 200, and then what you find out is the x bar, so the mean amount of average lifespan in those 200 people was 83. Yeah, so let's say 83. Okay, so in the sample is 83. So the idea here is that, okay, and then standard deviation is 8.1. So this is the standard deviation of the sample. Okay, I'll change that to sample. Okay, so these are all of the statistics of the sample. Okay, make sense so far? Yeah. And currently 80 is the main hypothesis that you're like, okay, it's around 80, so it's normally distributed around 80. But we don't actually know what the standard deviation is for the 80 here. So like, if you do 1, 2, 3 standard deviation, what are these values? We don't know. Okay, and so in order to estimate these values, you would use the formula. Remember, the formula has this section called sigma over square root n. Yeah, so this will be the standard deviation. So this is technically the standard deviation of the sample mean. That your teacher may or may not mention this. So remember x bar, right? That symbol is x bar. Yeah, so x bar is like the sample mean, and then sigma of subscript x bar is the standard deviation of the sample mean.
So that would be like you actually sub like the 1, 2, 3 into like whatever the mean is in on that graph.
On this graph?
Yeah.
Not yet, not yet. So what I'm saying is, if we're assuming that the actual mean is 80, right? We say we're assuming this is 80. So remember, the null hypothesis is that nothing changes. It's the same, which means it's still 80 years old, right? The average lifespan, right? The average lifespan is 80 years old, and now we need to find the standard deviation for this normal distribution, and the standard deviation is sigma over square root n, okay? Which is, in this case, 8.1 over square root 200. All right, let me calculate what that is. Then, so, okay, so 8.1 divided by square root 200. So this is about 0.57, or let's say 0.6, make it a bit simple. If it's 0.6, it means that, like these three ticks, you say that this would be 80.6, 81.2, 81.8. Right, and then you go backward, it will be 79.4, 78.8, yeah, and then 78.2. Okay, so now looking at this, right, again, the main assumption is that the average lifespan is 80 years, right? So the mean, maybe I'll write the mean over here. So I'll start using mathematical symbols. So the mean of the hypothesis is 80 years. Right, we're assuming this is 80. Now the claim is that it's no longer 80. Right? It's no longer 80, and when you, so let's just say we pause here and think about it. So in the sample, the mean is more than 80, right? But the question is, how likely is it? How likely is it that you actually get the mean is like that you get the sample mean is 83, considering if you're assuming the actual one is 80, okay? So in this case, 83. So you see, once you've calculated the standard deviation of that curve there, where is the number 83? The number 83 would be like 4 standard deviation, 82.4, and 83 is like 5 standard deviation away. And remember, the area, the majority of the area falls within plus minus 3, so it becomes very, very small. So now the question here is, at the number 83 here, how likely is it for you to get this number if the mean is 80? It's not likely, right? It's so far along that edge. It's like almost not, like it's like 0.something% chance, right? That you do just one experiment and you instantly get like 83. So this is like equivalent to, okay, actually I'll use a different example later, but you see, based on this, you can already tell that, okay, because the sample mean is 83, right? It's way to the far right here. So most likely the null hypothesis, aka the average lifespan is 80, is wrong, rejected, right? Make sense? Okay. Now, but in this case, right, we can see that 83 is like way far to the right, right? But we need to have a more like mathematical way of determining it. So the mathematical way is using the significance level. Significance level. Okay. So how does the significance level come into play in here? Well, the significance level, let's say the question is 99%, right? So let's say the significance level is 99%. What does it mean? And they're claiming that the average lifespan is more than 80, okay? That means that in this graph, in this this normal distribution here, I am interested in what, like any value post a certain area where the area to the left is 99%. Okay, so the area to the left of that value must be 99%. So this significance level is saying that this test statistic, right? Test statistic is the one that I think the teacher will mention about calculating. This test statistics, the area to the left of that is 99%. AKA, they're saying that, okay, as long as the chance of getting that sample mean is within the 99% area to the left of that value, it's acceptable. That it means that the null hypothesis is not rejected. Does that make sense?
How do we know the test statistic?
Yes, good question. So the test statistics is, let's say if it's there, right? And remember, this curve is like the same, right? All normal distribution curve can be resolved to the z distribution curve, right? The standard normal curve, right? So that would be like 1, 2, 3. I don't know, maybe a little bit more than 3. I think 99.7 or maybe between 2 and 3. I think. So, but then we don't know where it is. Now we just know that the area to that z value on the z curve is also 99% or 0.99 or let's say 99%, which means using your table it will be 50% here. Therefore, the table you need to search for 49%. Okay, now let's search for 49% in the table. No, that's from this first one. Do you have the table with you?
Yeah.
Yeah, we'll search for that in the table. Okay, so find me the z value for 49%.
0.49.
0.49, yeah. I think there's something that is exactly 0.4900.
0.4901 and 0.4898.
Then the 4901 probably the closest. What is it?
2.33.
2.33?
Yeah.
Okay, so this one is 2.33. Now, 2.33, I think your teacher actually gives you the value for this moment. This is one tail test, right? Because we're looking at only the right tail, and that's 2.325. So pretty accurate, right? Okay, so 2.33. I said we use the value 2.33, right? So this z value is how many standard deviations away is the number that's 49% area here, right? And we also want a number that is 2.33 standard deviation away, which means the test statistics is 80 plus 2.33 standard deviation away. What's the standard deviation? Well, it's just the sigma over square root n, right? And we already calculated that. That's roughly about 0.5728. 0.6, but I'll use the actual value. So if you actually calculate that, so 80 plus 2.33 times by that is 81.33. Okay, so they're saying that the value 81.33 here, right? So the test statistics is actually here. So 81.33, 81.33 is the test statistics, and the area to the left of that is 99%. Okay, so they're saying that, okay, if you take a sample of 200 people, right? If you take a sample of 200 people and you get any average age of less than 81.33, it's within the 99% predicted level, right? So 99% of the time, you will get the sample mean to be, you could get like 80.1, right? Sorry, you could get 80.1, which is here, or you could get 79.6, which is here, or you could get even 78.0, which is here. But remember, the further away from the mean it is, the less likely it is. But we don't care. Even if you get 75, that's okay, right? Maybe it's just a rare event, but then again, it might be testing a different one. So even if you get, let's say, 81.2, right, which is higher than 80. You see, it's higher than 80. But if you get a number like 81.2, it's not significant enough to say that the mean is no longer 80. It's not significant enough. It's still within the 99% accepted level, right? But if you get a value like 81.8, for example, it's outside of the range 99%. That means that if there is less than 1% chance that you get a sample size, a sample mean like that, right? It's less than 1% chance, which means that, so let's say if we get 83, right? Because the sample mean is 83, there are two things that could have happened. So the first scenario is the hypothesis is correct, is 80, but it is a super rare event where it's like the probability of that event happening is like 0.001% or something. Or scenario number 2 is the mean is no longer 80. In fact, the population mean is probably greater than 80, right? Because if you shift the expected, like the hypothesis over here, then there is a greater chance that it will have the value 83, right? So then it's saying that, okay, the mean is probably greater than 80. We don't know how greater, but it is significant to prove that the mean is now greater than 80, the average years. Does it make sense?
You know, just practice a few questions and then see.
Okay, I'll give you another example. This actually don't really like this example so much. I'll give you another example. So let's just say if you okay, if you guess, so let's say you take 100 playing cards, right? Okay, 100 playing cards. Okay, and then I'll pick a card and you have to guess the suit of it. Is it a spade? Is it a club? Is it a heart? Or is it diamond? Right? So the chance, the probability of guessing the correct suit of cards is roughly 1/4, right? Yeah, but every time we do the experiment, it will vary. Sometimes you guess, so the expected value is about 1/4 of 100. So I expect you to guess about 25 correctly. Make sense, right? So, but sometimes when you actually get do the experiment, sometimes you get like higher. Sometimes you guess correctly 27. Sometimes you guess lower, which is maybe only 20, right? But let's say if I claim that, James, I have clairvoyance. I can guess better than random guessing, and we do an experiment. You show me, we do 100 cards, and I guess the number, and I get the number like 28, right? Or 29. Okay, and I'm like, see, I guess higher than the average, right? The average is about 25. I should get 25 correct, but I got 29. See, I'm better than average. I have clairvoyance. How do you prove that? Right? How do you prove that? The likelihood of that. So in this case, we are expecting that the mean is 25, right? And now I need to prove that my guessing is better than 25. Right? The average of my guesses is higher than 25 because I have clairvoyance. I should be able to guess higher than 25, right? But in order to prove that, I need to, with a significance level of 99%, right? That means that the area to the left is 99%. I need to show that my guess, which is 29, is way, way higher than the test statistic, which indicates 99% of the time I will guess between those values.
Does it have to be 99?
No, it can be 95. Normally it's 95. But in some questions they may ask you 99 or they may give you 90. That's why the table here they give you the t value, or it should be the z value. I don't know what they call t value. So the z value, they give you the z value either for one tail or two tail, and then it will be 99, 95, or 90%. Okay, so you could be asked any. The idea is that it's just like how 99% means you're 99% sure most of the time that the sample mean will be, like when do the experiment, will be between those values 99% of the time. Okay, so let's say if we use the 95%, for example, let's say 95%. So I'm like, okay, as long as I can do better than 95% of the time, then I can prove that my guesses are better than average. But let's see. So again, the standard deviation is what? Of the sample mean is sigma over square root n, right? And in this case, we will use the sigma. So let's just say standard deviation is, I just need to make up one. Can't remember what was a good one. Let's say 2, I think. 2, 4, 6. Okay, let's say standard deviation is 0.6. Okay. So 0.6. Okay, yeah. So the standard deviation is 0.6, so that will be 0.6 divided by, or let's say 2. Let's say 2. So 2 divided by square root of 100, right? Which is 2 over 10, which is 0.2. Yeah? Now, just at this point, do you think my guess is, actually, I think the standard deviation should be a little bit higher. Let me see. It could be 20. Yeah, sorry. Let's go with 20. I have to adjust the numbers a little bit. When you actually do an experiment, you can try it with your friend. You can do an experiment and actually get a normal, like a calculated standard deviation, and it will make a bit more sense. I'm just making up numbers to illustrate my point. So bear with me. All right. Let's say 2. Okay. So 20 over square root 100 is 2. Okay. Now, with this standard deviation, okay, and the 95% significance level means that the area to the left is 95% also on the standard normal, right? And it's a one-tailed test, which means the z value will be, I think, for 95% one-tail is 1.645. Okay, so a value that is 1.645 units higher than the mean 0 would have the area to the left 95%. Okay, and so this value here should be 1.645 standard deviation higher than the mean 25. So it will be 25 plus 1.645 times by standard deviation, which is 2. Okay, and add that in, that would be about 3.29. Right, plus 25 would be 28.29. Let's write that down here, 28.29. Okay, so let's say given this experiment here, so this value 28.29, if I can guess better than this, that means I actually can guess better than the average. And because my guess was 29, that means that the number falls into an area that only has a 5% chance of happening, right? Higher than 28.29. So it means that the hypothesis has the null hypothesis of 25 average is rejected. Right? It means my guess is actually a little bit better than average. They shift it to the right. Does that make sense? Yeah. If I can guess 29 correctly, right? Obviously, I'm going to get most likely we'll get like 27 or lower, right? So most likely that number there should be could be like 27. I don't have clairvoyance, so I might be able to guess 27 instead of 25. And 27 is still lower than the test statistic 28, so it will fall into the area that is most of the time, 95% of the time, it could happen. So it's normal case. You can't reject the main hypothesis. Does that make sense?
Yeah.
Okay. So now I'll based on that, I'll show you the actual working out for this one here. Okay, that I'm pretty sure your school will accept. So random sample of 200. So n equals 200, right? And then the average lifespan of 83 years. So the sample mean x bar is 83. All right. And the standard deviation s, we write s is 81. I don't know why they use s. Nobody uses s. Anyway, your teacher formula uses s, so I have to use that one.
Well, I think it's because we never use these symbols, and because it's
like the sigma.
We only use this one. It's the first time. I think s is like standard deviation, so it would be easy to remember.
Oh, okay, yeah. But the mathematical symbol is sigma. If you go online, it's always sigma. That's okay. I'll use s. So s for standard deviation 8.1, and then okay. So remember. Now continuing reading at a 99%, so the alpha level is 99%, right? Does this indicate that the average lifespan is greater than 80 years? So remember, the 80 years here is the main hypothesis. So the mean of the hypothesis, or H0, is that, so the null hypothesis is that the mean is 80, right? Or because they say greater than 80 years, you can write this is less than or equals to 80. Right, but normally you test it against the value, so I'll just write equals to, I think you might need to write this, but anyway, it's just saying that it's around 80, and I don't care about when it's lower. And the alternate hypothesis is the mean is more than 80, like that. Make sense so far? Yeah. So see, that's where the null hypothesis comes from. It means it's no change, right? Even online, I double check with many sources. Everyone said the same thing, that normally you just go mean the null hypothesis is equal to 80, right? So you assume the mean is a certain value, and then you're trying to prove that the mean is actually greater than that value, right? But anyway, some sources they do write this, so I'll write that for here. Okay, so now we need to, so because the mean is at 80, right? That means less than or equals to 80. So I'll draw the standard deviation where it's 80 here, right? And then the test statistics, right? Let's see how they write the test statistics in the explanation. Oh, critical value. Okay, yeah, critical value. Okay, so the critical value is somewhere here, right? Because you're trying to prove that it's greater than 80. So you're going to look at the area that's greater than the critical value. Make sense so far?
Yeah. So if it falls into the red area, it will prove that the hypothesis is wrong.
The null hypothesis is wrong, yes. So you reject the null, yes.
Yeah.
So you prove that one wrong. Yeah. So now the critical value is how many, because we want 99%. So the area to the left of the critical value has to be 99%, right? And corresponding to 99%, the z value at 99%, or whatever the T alpha is what your teacher would write. T alpha would be, I'll use that table so you can see how to use it. So it'll be one tail test, 99%, so that's this one here, 2.325. So right, T alpha equals to 2.325. Remember, this is basically just the Z value of 99%. Okay, so standard normal 99. Not sure if your teacher would tell you how to use that table to find the T alpha or the Z value. If they do, that's good. If they don't, at least you know how to use that. Okay, see if you can teach that to your friend. See if they can actually make sense of it. Anyway, so yeah, so T alpha is 2.325, so that's just 2.325 standard deviation away from the mean. But you're gonna get the standard deviation. What's the formula?
Sigma over square root of n.
That's right. Which means the critical value, right? Critical value, they just give you the formula, but now you understand it. The critical value is, starting from the mean, you need to add a 2.325 standard deviation away from the mean. And the standard deviation is sigma, which is 8.1, or S, over square root n, which is square root 200. And that's how you get the critical value. And now you calculate that. So 2.325, I use these values, 8.1 divided by square root 200. So that would be critical value is 81.331, right? So now this one is 81.331, and then since the sample mean, which is 83, is greater than 81.331, right? There is, you gotta write the conclusion, which is there is significant evidence to reject H naught, okay, at 99% significance level. Okay, so that's generally how you write it. Now let's see how the teacher actually writes it. We can reject the null hypothesis and conclude that there is sufficient statistical evidence at a 99% significance level that the average lifespan today is greater than 80 years. Yeah, just repeating it. Okay, so you reject H naught and then you've got to write, you accept the other one, aka the average lifespan is greater than 80 years. Right, make sense? Okay, does it make more sense?
Yeah.
You sure?
Yeah, it makes much more sense.
Okay, all right. Now let's work through one example together. I will give you this one.
Oh yeah, and for this one, like the triple one, is there a shortcut? So you don't need to like use all of these. I know there's a shortcut for like the 2, but I'm not sure about 3.
I don't think it's a shortcut. You have to do the first 2 and then you have to do the other 2.
Oh, okay.
Yeah, you can't. Yeah, there's no shortcut for that. If they're not the same, then no, you can't do anything about it. Okay, actually one more thing. I'll explain the two-tailed test first. So that was the okay. Let me explain these ones. So that was the right tail, right? Now read this question here. It is claimed that the average distance the car covers in a year is less than 20,000 kilometers. Okay, and then to test this claim as a random sample, blah blah blah, result revealed that the average distance is 19.200 and standard deviation is is 3,850. Use a significance of 0.01 to test this claim.
I think I can guess how to do this one.
Yeah, how would you do this one?
Would the critical value be the same as the rat tail test?
What do you mean by the same as the
So
right
like
tail
the table, there's like a 2 tail and 1 tail. They will all be the same. They will all be like 1 tail test.
Yes, but it will be negative because you subtract from the mean. Right? It's to the left hand side.
Oh.
So you take the mean and you subtract that.
Oh,
right?
So it's like the same thing where right hand side is just plus n and left hand side is just minus.
Yeah. Yeah. Okay. Yeah. Good. And then the two-tailed test is
You plus n minus. Like, but you have to like use the 2 tail one.
yes, you have to use the two-tailed one. Why? Because you're saying the area in the middle is 95%, but then you consider as long as this falls in either the right hand side or the left hand side, either area you will reject them. So 95 in the middle, so 5% to reject, so 2.5% reject, 2.5% reject.
Okay. Oh, that's why it's different.
Yeah, and the two-tail test is like, so look at this one. The key word is skeptical. Okay, so they claim that the mean breaking strength is exactly 16 kilogram, right? So they claim that is exactly 16 kilogram, and then a fishing magazine editor is trying to claim that it is not 16, right? Because 16 is in the middle. They claim it's not 16, which means that it could be higher or lower. That's why you have to split it. Either higher you reject, or lower you also reject.
Okay.
Yeah. So if the value falls into this region, reject. This one also reject, right? Because previously we only care about whether it's higher. Yeah. Okay. Yeah. So that's a two-tailed test. Does it make sense? Okay. Let's try one question.
Will it say whether it's two tail or one
No.
tail?
You have to deduce. You have to think whether it's one tail or two tail. Okay. So one tail test is when they are claiming that something is higher or lower.
Will it say that is?
Yeah. They would. So for example, read question 1 here. All right. Let's try this one. Okay. I will also give you the table for the T alpha values things. Okay. Right, try this. So first, is it one tail or two tail?
One tail.
One tail, okay. Left tail or the right tail?
Left.
Yes, good. Because less than, right? Okay, good. Calculate. Tell me what the critical value is.
Okay. In the actual thing or just said?
The actual value that you compare, and then make a conclusion. Whether you reject or accept the null hypothesis.
I can't remember what times like the equation.
So in summary, the formula is you take the mean of the hypothesis, and then you plus or subtract, right? It will always be the z value or the t alpha value and sigma over square root n.
Oh, that's it. 90. Is it 3006?
Yes, that's right. Okay, so what's the conclusion? Do you reject the null hypothesis?
Yeah, reject.
Reject, yeah, because it's lower, right? Try to calculate again with 99% confidence. What would it be with 99% confidence?
2,900?
Yeah. So would you be able to reject with 99% confidence? No. Right? So you see, sometimes it happens this way, and this is, I think this is a question that brings up a point where when you see statistics in newspaper, right, it has been played around with quite a lot. Okay? If you change the confidence level from 95 to 99%, suddenly you can't accept, you can't reject the null hypothesis anymore. Which means if it's like at 99% confidence, you can't say that the debt is lower than 3263, so 62 anymore, right? Because 99% of the time it could happen, right? There is a small chance that it could happen, but it's still not small enough to be rejected, right? It's not like the less than 1% chance.
So like the 99% would be the strongest one?
No, you can go 99.99%.
Oh.
Okay. Now it brings me to a point. I think I mentioned this. I might have mentioned this about. Did I? Maybe. Okay. So let's say 99% of the time. Let's say if you go buy McDonald's, right? McDonald's, and would you accept 99% of the time the burger is good? Is it good enough? Yeah. Okay, it's good enough, right? Or would you accept 95% of the time the burger is good enough? So out of 100 trips to McDonald's, 5 of them the burger is kind of meh. Is it good enough? Yeah. Would you accept a pacemaker that works 99% of the time?
What is a pacemaker?
Pacemaker is the one you put in your heart. If it stops, you die.
Oh.
Would you accept a pacemaker that works 99% of the time?
Probably like 99 point something.
Yeah. Because 99% of the time, what does that mean? It means out of 100 days, one day wouldn't work. Right? It will fail one day. Every 100 days. Okay? Would you accept that? Probably not. You may accept 99.999% only. Right? Because then out of 100,000 days, then it will fail one day. 100,000 days, how many years? It's roughly every 273 years, then it will fail for one day. Right? Then you would accept that level. Right? So yeah, it's a game of statistics, right? Sometimes you accept a lower one, sometimes you have to go really, really high. Depends on how critical it is. Right? So yeah, that's the idea about different level of confidence. Sometimes it's good enough for business, sometimes you can't accept anything less than 99.99%.
Okay.
Right? Interesting? Yeah. Yeah, good. That's it. That's hypothesis testing. Hopefully that makes sense.
Does my school do it in this way as well? Or
Yeah. I'll show you the formula from your school. They will just show you the formula and be like, oh yeah, punch these numbers in. So I'll show you the calculations here. Now you read it, it makes sense. Right? Actually, yeah, they do use the mean equals 80 years. Yeah, that's fine. You can use that. Mean equals 80 years. And then the other one, mean is more than 80 years. You see they use the H, the mu H, which means that's the mean of the hypothesis. Right? That's the hypothesis mean, which is 80 years. So now it makes sense why we use 80 years. Right? That's the one we're trying to prove. Okay? And they just punch the whole thing in, get the answer, get 81.33, and then they conclude.
Oh, so they don't really explain everything. They just sub it in and that's all.
Sub it in and get the answer. Okay, that's why. Okay, I'll show you the other way of doing it. You don't need to do it, but I'll show you the other way that I keep on mentioning that it makes more sense to me. So the other way is this. So using this same thing, right? They actually use something called, remember standardization in normal distribution? The standardization formula. Wait, have you learned this? Standardization formula. So the standardization formula is Z equals to X minus mean over sigma.
Oh, I think so, yeah.
Yeah, right? Okay. So note that sigma is sigma of the sample mean, which is so the X bar and then minus the mean of the hypothesis and divided by, it would be the sigma over square root n, right?
Oh, is that equation like converting the actual value into like the 1, 2, 3?
Yes. And then when you look at so once you've got that, right? So let's say in this example, well, not this one, but let's say you use this example here, right? Then the value would be, X bar would be 2995, I think, right? And then subtract 3262 over the standard deviation is, what was it? 1,150 people. So 1,100 and then square root 50, right? So this would be the Z value. Okay,
It's kind of like calculating backwards and then converting it into the Z value and just compare it with the table.
Yeah, that's right. Yes, that is correct. So this one would be negative 1.716. Okay, and then the table Z value was, what was it again? 1.6 to 1.645, was it? Yeah, 1.645 or minus 1.645. Right, so it's like saying, okay, if you standardize that value, the sample mean is corresponding to about negative, that value is negative 1.7 to the left of the mean, right? Standard deviation to the left of the mean, and the critical value that we found was negative 1.645. So then this value corresponds to the value over here, which is negative 1.716. So that falls in the 5%. Yeah, the 5%. So you reject the null hypothesis. But when you're looking at 99%, so the 1% area is on this side, right? So the 1% area is here, and the number that at the 1% area is negative 2.325 or something. Yeah, negative 2.325. So that value is in between the mark, the Z value for 5% and the Z value for 1%. So if you go 95% significance level, you reject it. If you go 99, you can't reject it.
Well, would that be a question like whether this value falls into like a certain percentage?
You can find it.
Yeah, because just that falls into like the, what is it, 4?
Can you find it? Can you find it? What's the percentage
of the number?
Can you find it? You can find it using that table.
This one?
Yeah. Alright, make a guess. How would you find it? Hint, you don't use the number negative. There's no negative in there. But
it was the same thing, just
that's right. Yep, correct. Yeah. So see if you can find it.
What is the 1.716?
Mm-hmm.
This is only up to 0.4.
What was it?
0.4998 is the biggest one.
Yeah, but you're not looking at the, remember this is the Z value. This is not, that's a probability. We're looking for the probability.
I'll just need one.
Yeah.
Let's round as it'll be around like 45%.
45%? Okay, 1 sec, give me 1 sec. So
what is 0.5 minus? .27%.
4.27%. Okay, give me a second. So lower is negative 999, and then upper is, yeah, you learn how to get this from the calculator later at some point. What do you say?
4.27.
27? It's about right. Yeah, it's actually 4.998%, so about 5%. Just below 5%. Yeah, makes sense. It's just below 5%.
But it won't be in the exam, right?
I mean, if you give the answer in the exam, it could be an exam because this is actually this week's content, week 1 or last week's content, week 1 content. They ask you, oh, if the Z value is this, what's the probability? So they would ask like, what's the probability that Z is lower than negative 1.72, for example, right? And then you would use 1.72, read that out, and you would find the right hand, the error in the middle here, and then you have to go 50 minus that, right, to get the error to the right hand side, because that will be the same as the error to the left, yada yada. Okay, so yes, you will be asked this question, right? Because that's just actually week 1. It's not even week 2. All right, make sense?
Yeah.
Okay, good. All right, so yeah, that's hypothesis testing for you. Go back and do some practice, okay, and I think you'll be okay. Now let's move on to, so I think that's the end of this week. So now we move on to next week's content, week 3. Okay, so week 3 content is matrices. It's one of the most interesting structure of mathematics. Matrices and vectors. Those are the interesting. Have you learned vectors? No? Okay, you will learn vectors. But anyway, so matrices is the idea of having of displaying numbers in columns and rows, like a table. You used Excel before, right? It's like Excel, right? Think of it a little bit like Excel. So for example, right? Let's say let me find an actual example from your textbook or from your notes. That one. Okay. Matrix and matrices. So let's see. Skip these ones. Oh, this one.
Is this harder than like the Wk2 content?
No, Wk2 is the hardest. Conceptually is the hardest. Like this one's is easy. I think you'll find this like pretty easy. It's just a bit like just algebra. Okay, all right. Okay, so let's say we have this information here. Okay, let's say exporter. Okay, ignore the stuff on top. Just look at this line here. Exporter A sold 120 refrigerators, 95 CDs, 370 washing machines, and 250 televisions. And exporter B sold a bunch of whatever. And then there's exporter C and D. Right. So if you look at that information there, how do we represent this in terms of like a table? Let's say a table, right? A table, you would do, okay, that's exporter A and exporter B, and then you would have refrigerators here, CD here, and then washing machines here, and then televisions here. And then you put the number A is 120, and then 95, 370, and 250, right? And this is 430, 380, 1000, and 900, right? You somewhat put it like that as a table. Now, the way that we're displaying the numbers in rows and columns, see this is like a row, right? And then this is like a column, right? Displaying data in a rows and column like this is exactly what matrix is about, like that format there. But you would write this, let's say called the matrix M is equals to, and then you would use a square brackets here, and then put the numbers in the exact same order. Right? Make sure you put a space in between. It's like, imagine if there's like a line to separate them, but we don't draw the line. Okay, so that'll be 430, 380, 1900. Actually, I'm planning on going through not just the basic matrix stuff, but I'll go through week 2, 3, and potentially 4. Because week 4, when you learn about matrix multiplication, that's when like everything comes together. It's like, oh, this is why you use matrices to represent data, because it makes some calculations a lot easier.
How do we multiply this like bunch of numbers?
Yep, I'll show you. Okay, so so this is the idea of a matrix, right? Is you represent it in rows and columns. So how many rows?
2.
2 rows, right? How many columns?
4.
Okay, 2 rows and 4 columns. This is a 2 by 4 matrix. You count the rows first. Okay, so a matrix has dimensions. So 2 by 4 matrix means 2 rows and 4 columns.
Will that make a difference in the calculation?
Yes, it does. In week 4. That's why I want to get to week 4. If we can wait to week 4, we'll see. So if it's a 2 by 4 matrix, it will look like that. What do you think is this matrix here? Let's say 1, 2, 3, 4. Right? What is this matrix, the dimension?
2 by 2.
2 by 2, right? Pretty easy. How about a matrix that looks like this? 1, 2, 3.
1 by 3 or just 3?
Yeah, 1 by 3, good. So remember, it's like when you read in dimension, it's like a door, right? If it's 1 meter by 3 meter, you don't say 3 meter. It's 1 meter by 3 meter. Right? So the same with the matrix. The dimension is 1 by 3. This is called a row matrix because there's no row matrix or column matrix. I think it's a row matrix. There's
only one.
Only one row, yeah. I think.
Is there a column matrix where they only have like one column?
Yeah, there is. Yeah. So column matrix is when you have just a single column, right? And then now a zero matrix has 0 for all elements. Okay? Yeah?
What will the zero matrix happen?
When would it happen?
Yeah.
When you do matrix subtraction and addition. Now, good point. Let me show you an example. So matrix has arithmetic. So similar to how when you do 3 plus 2 equals 5, when you have a matrix that has, what's the dimension of this one?
1 by 1.
1 by 1, yes. So when you do matrix of one number plus matrix of two of the number 2 is the same as a matrix of 1 by 1, which is just 5. But what do we do if there is more than one dimension? Let's say 1, 3, and then plus another matrix, that's 2, 4. What do you think the answer is? I haven't showed you what it is yet, but intuitively, what do you think the answer is?
3, 7.
Yeah, 3, 7. You just add the numbers on the same position together. That's it. Okay. So if you have a number like a matrix like 1, 2, 3, 4, and then you add it to a matrix of 5, 6, 7, 8, what's the answer?
Do we add the 2 in the bracket or just keep it at the same position?
Tell me what the first number is. I'll tell you the hint. The answer, there will be 4 numbers in this matrix. It's the same 2 by 2. It will be also a 2 by 2 matrix.
6, 8, 11, 10, 12.
Yeah, that's right.
Oh.
You just add the number in the same location, right, of the matrix. That's it. Subtraction is the same, right? If you have the same example and then you do subtraction, you just subtract it. So the answer will be?
Negative 4.
Mm-hmm.
Negative 4.
Mm-hmm.
Negative 4. Negative 4.
Yep, because that's just increase all numbers by 1, right? So of course the difference is going to be the same. So yes, it is a matrix where it's all negative 4. So of course, if you get this matrix and then you plus it to 4, 4, 4, 4, then you get a matrix that is?
0, 0, 0, 0.
Yeah. So this is the 0 matrix. This is a 0 matrix 2 by 2. Okay? That's the end of week 2 and 3 content.
That's the end?
Of week 3 content, yeah, that's all that they're going to teach you in week 3.
Oh, I saw like a bunch of other stuff. I thought it was like hard.
No, it's just, so this is like, if they are equal, then of course the values in the same position will be the same. X is negative 3 and Y is 4.
Will that just be X minus 3?
Yeah, X is minus 3, yeah. You would write X equals minus 3. Yeah, like these things are easy. I think you'll get this straight away, so I'm not gonna bother going through it. Okay, so representation, I think these ones are the one that I will let your school, let you practice that with the school, but basically it's just representing the data in a matrix format, right? So like 4 rows of seats, of 3 seats, each in a minibus. 0 is the seat that is vacant, and 1 is the seat that is occupied, right? A matrix. So first and third rows are occupied, but the second and fourth row are vacant. So first and third row are occupied, second and fourth are vacant. And then B is like only the seat on the front left corner of the bus is occupied. So front left corner. And then the rest is unoccupied.
Where will we use this in real life?
That's why I will get you to week 4 content. Okay.
Oh.
Next week's content is, I think it's a bit like too mathematical. I would prefer to group a few things together and then do week 4. But I think they're splitting up to learn the algebra first. But I don't think it's as useful. Normally, I would go straight to the multiplication first. Yeah, now I'll skip this one. So this is lesson 1 on matrices, and then the next 2 lessons that you will get at school is just addition. It would just be addition and subtraction, which is exactly what I just said. Just add and subtract, right, at the same location. And then the recap is just more practices. So that's not what I actually want to go into. I want to go into this one here, multiplying matrices.
Would it be different? Would it be different with like the addition and subtraction?
Quite different. There are 2 types of multiplication for matrices. Okay, I'm going to borrow here. I'm going to borrow this one here.
Oh, I was wondering why the houses are the same as my school, and I just realized it's my school's house.
Yeah, this is your school PowerPoint. I will use a school PowerPoint so that when you go to school, you get the same content again. And the idea is that if you know how to do it already, when you see it at school, what do?
Just do it again.
Just do it again. Just do it before your teacher even gets to the end, if you can.
My teacher uses like a stupid method for like week 1 content.
What does she use?
You know
he or she?
She.
Oh, what does
you
she
know
use?
like the where you can just 50% minus like the Z value. I think she did like a whole bunch of work. She did like 1 minus 0.5 and then it would be it was 1 minus bracket 0.5 plus the Z value bracket. Yes.
Yeah, that's funny. Oh well. Does she teach actual specialists or does she only teach year 10?
I think she teaches actual special. I'm not,
Really?
yeah. But
Does she teach methods?
I think so.
Oh, okay. I don't know. That's why I see the notes in your thing and I question that a little bit, but that's okay. It's fine. You'll be okay. Yeah, I'll make sure you'll get the main content. Anyway, so have a look at this one. This is week 4 content. Okay? Week 3 content is pretty easy, but week 4 is the one that's a little bit different. So Excel, simple Excel, right? If you want to find, okay, this is the result of a sports carnival. Let's look at the first row here. Let's focus on the first row. Atunga has 60 people in the first position, and 63 in the second position, and 51 in the third position, right? And then for each position, these are the points per position. You want to find the total points, okay? You want to find the total points for house Atunga.
Oh, so that's how a school calculates our points.
Yeah. They would put into Excel. Well, they would use some form of matrices, but of course they use software, so they don't actually do matrices.
Type in the code and just get the answer.
The advanced stuff in matrices, you will learn some really interesting one. Math specialist, unit 2.
Oh, so I have to still wait for like year 11 and 12 to learn all this stuff.
All the cool stuff, yes. Yeah, like year 10 is like a foundation. But now, what I'm thinking is, if you're okay with the school content, I'm going to start teaching you year 11 and 12. Because math specialist, if you're aiming for like the 90-something%, 100%, by the time you do it at school, you need to already know all the basics. And you're just doing like complex familiar and complex intermediate. Because those other ones are really hard. Some questions, it makes me think a little bit. Most of them I can just do straight away, but some, it makes me think a little bit. Those ones, I think you won't be able to do straight away. Okay. So I want you to get to that point. That's why I'm like, this is week 2, right? I'm going to week 2, 3, and 4 content. So by the time we hit maybe halfway through term 3, we're done with term 3 content. So then I can start teaching you like specialist year 11.
Yeah, I think that's still term 4.
I know, but we don't know what term 4 is yet.
Do
you?
Yeah, I think I do.
Oh yeah, but I don't want to teach you ahead too much. So maybe a couple of weeks before term 4 starts, during a holiday in term 3, I might teach you the term 4 content. But if I teach it too early, by the time you reach term 4, you might have forgotten. Yeah, but I'll start, like for example, these matrices, right? Because this term is the thing is the confidence interval and as I said, hypothesis testing, you won't see that again, but confidence interval, you will see that in unit 4 of methods and specialist. Okay, methods and specialist, you see that again. It's a small section of specialist, but it's a big one in methods. Matrices is a big one in unit 1 specialist. That's why once I'm done with all these matrices in your term 3, I'm gonna start you on year 11 content, also matrices, so you can see like how it applied in some practical applications. Because I think in this one you only learn the basics, you won't get too many practical application ones, I think. Yeah.
A lot of people say that in senior methods is harder than specialist.
Senior methods?
Yeah.
As in year 12? Or like just 11 and 12?
I think 11 and 12.
Or you mean 11 and 12 in general? Yeah, yes and no. Methods at the start is harder than specialist, but specialist unit 4 is really hard. Yeah. But then the thing is, I think they say that because when you're learning like many content you need to learn in specialist, you already kind of pre-learn that in methods. So you learn like the basics in methods and then you apply that for specialist. But the application part is not as hard as the initially learning, right? When you're initially learning it, is methods. That's why it gets hard. So yeah, so method is, some people do say that it's harder than specialist, and I do agree to some extent. Yeah.
Is the hard part about like the understanding or the actual calculation?
The calculations. I think understanding it is hard only in unit. Starting unit 2 could get a bit hard, but I think you should be okay. But unit 4 is the hardest about understanding. But the calculation is always very difficult. The algebra for an average student. Maybe you'll be okay. I don't know. We'll see. Yeah, but calculation is very difficult. Like the algebra, a lot of students just either mess up or have no idea how to continue from certain parts.
Oh.
Quite tricky. Anyway, so okay, so let's say for a Tonga, right? In order to calculate how many points, you would do 60 times 5, right? And then plus 63 times 3 points and plus 51 times 1 point. Make sense? Right? So what you're doing is, now if I were to visualize that, what you're doing is just basically taking that row and multiply by this column. Right? So you take this row and then you multiply by that column. But you take the first, multiply by the first, second, multiply by the second, and third, multiply by the third.
Why don't they put that in rows as well?
You mean like this one here?
Yeah.
Because this is the best way to introduce you to matrix multiplication, because you also do row times column. These two are matrices. Okay, these two are matrices. So if you were to take 60, okay, let's write the first row only as a single row matrix, right? When you times it by the column 5, 3, 1, the answer will be, well, when you add all of this up, that'll be 300, 189, 489, 53540. Okay, you get a single row and column matrix representing 540.
Will it always be first one times first one, second one times
Yep.
second?
Yep. But what if I expand this matrix to include the next row, 71, 64, 74? What do you think?
2 by 1?
2 by 1. Yes, that's right. It will turn into a 2 by 1 matrix. That's right. Okay, and how do we get that? How do we get the new number? It's the same thing. Is this, take the horizontal one times the vertical of the other one. Right? And then that will get you the next point. That make sense? Yeah. So why do we represent it in this way? Well, the reason why we do it this way is because what if, you see, this is a point for, let's say, school A. Right? So in school A, the point system is let's just say in January, the point system is distributed that way. But what if in February, the point system is distributed a little bit differently, right? Let's say in February, it's 6 points for first position, but only 2 points for second and 1 point for the last. How do we recalculate it? How do we represent this? Well, it's actually the same thing. You just need to add another column here. So when you multiply that, right, you will take this one times by the first column will be 540, and then you do this, but you times by the second column, that will get you the second column of the first row, right? And then, well, okay, let me just quickly calculate that one, just to give a representation. Is 537. So in February, that point is only 537 instead of 540, given the same like exact position were recorded. And then you take the next row, right, times by this, you would get the value here, and take the next row times by that, you get the value here.
If there's like a second term for the first matrices, how would you write that?
What do you mean by second term for first?
So you know how like those red set of yeah, that one's for the first term or whatever. Like for January.
Okay.
And then for February, they got like a different score, like maybe 60 something for first place, and just other numbers for like second and third.
Good point. So that would actually need to be represented as a separate. You probably need to do a different matrix. Oh. So again, matrix design is a completely different area. Okay, you need to design the matrices when you have more than one data. So this is a two-dimensional matrix. 2y is like 1 dimension here, 1 dimension here, right? Sometimes you might have a 3-dimensional matrix. You won't learn that here, maybe in university if you do engineering.
Oh, so not that in high school?
No, it's too complicated. You can't visualize 3-dimensional matrix, but you will use that quite a bit in like even like 4-dimensional, 5-dimensional matrices. If you do data science, you do a lot more of that. Yeah, pretty interesting. I didn't get to learn too much of that because I'm not going down the data science pathway. I'm just a software engineer. I focus more on building apps. But some of my data science friends, they did a lot with like different kinds of matrices. So matrices is very, very common used in engineering to represent data. So yeah, so in this case, we'll just do that, and then you just get the two values here. So if I were to punch that one in, actually, how about you try? Use the calculator. Find me value A and value B here.
So A would be 557.
What was it?
557.
557 sounds about right.
B would be 628.
Wait, one sec. How did you get 557?
71 times 6 plus 64 times 2 plus 74.
Ah, wait. When you times this with the second column, it's the second value.
Oh, you're saying B or?
Yeah. So, wait, 71 times 6. Oh, sorry. Yeah. That's 6 to 8. Yeah, that's right. Yeah, 6 to 8. Wait, can you calculate the first one again? I think it's not 557.
621.
Yeah, 6 to 1 sounds more like it. Yeah, I think you punched it in wrong, but yeah, that's alright. Get the idea?
Yeah.
Okay. So that's the reason why we represent matrices, and then you can do matrix multiplication. So you see, the only time that actually works is, see this matrix. What's the dimension of the first matrix?
2 by 3.
2 by 3. If you get a 2 by 3 matrix, what's the dimension of the second one?
3 by 2.
3 by 2. You can only multiply them if the two innermost, the two closest dimensions are the same. Do you see why? Let's say if we try to multiply.
I think I know why.
Yeah?
There's only like 3 numbers with 3 numbers.
Yes.
If that one's 4, then the fourth number wouldn't like time anything.
Yep, wouldn't times anything, that's right. Okay, so the easiest way to remember is when you do, this is matrix multiplication, yeah? So when you multiply a matrix with another matrix, the two dimensions that are closest to each other, like in the middle, has to be the same. Okay, so for example, I can just make up a dimension, let's say a 2 by 4 or 2 by 4 matrix can be multiplied with a 4 by 1 matrix. Right, so 2 by 4 means what? Let's say you got all these values 1, 2, 3, 4, 2 rows, 4 columns, right? And then you can multiply that with, now 4 rows is like, let's say 2, 2, 2, 2, but 1 column. Yeah, we can do that, right? For this, for that, you can multiply. Okay, so it's always horizontal, then vertical. All right, so yeah, so that's matrix multiplication. So this is something that's a little bit more new, right? It's a bit newer than the other one. Now, so that's matrix times a matrix, but you can times a matrix with a scalar. Okay, so put it this way. So for example, in a month, right? Let's say company, this matrix represents company A and company B, and this is how many cars, and this is how many say cars and motorbikes, right? So this matrix represents how many cars and motorbikes company A and B sold in that month. So it will be, let's say 40 cars and 20 motorbikes, and this one is 30 cars and 60 motorbikes. Right? If I were to say that next month, right? Next month, the sales of both were are actually double. How would we incorporate this information? So let's say this is month 1, right? We put a label on this one as the matrix for month 1. And then let's say for month number 2, how do we represent that information as a matrix expression? So that would just be 40, 20, 30, 60, and then, whoops, sorry, should be that. Double means times 2.
Oh, so you just write times 2 straight away?
Yep, or you just write 2 and then the brackets. Okay, so this one would just be literally written like that, and when you times it, so this is a scalar, it's not a matrix, right? Remember the one I showed you earlier, this is a matrix, that's a matrix. Right? So when you do matrix times matrix, you need to look at the dimensions. But if you have a scalar factor, which is a factor that's just a number, right? It's like double. You're just doubling everything. So this one would be equivalent to, right, the month number 2, double everything would just be 80, 40, 60, 120. That's it.
So that's a scalar?
That's a scalar, yes. This is a scalar.
What is a vector then?
Vector is, haven't learned that, so I'll show you. So scalar is a single number, right? Vector has a direction. So an example of a vector would be 2, 4. It's also kind of matrix-like. That's why you're going to learn matrix. Because to represent a vector, you use a matrix notation. So a vector 2, 4, I think...
How does it have like a direction? How does that...
Because the general convention is this is a vector represent the x and y. So it represents a vector that goes 2 in the x direction, 1, 2, and goes 4 in the y direction. If it starts here, it will go 2 there and 4 there. So the resolved vector in red would be this one here. Right? So this red vector is it has the length and magnitude. It's like an arrow, right? It has the length and the direction. So the direction, well, you'll learn a bit of vectors later. So this stuff, the vector stuff, is actually the stuff in specialist that gets a little bit harder in terms of algebra. Right. Most of my specialist students in the past, they struggle a little bit with this. Okay. So 2, 4 in the vector form is like in the x, y direction. But it's like a matrix. It's like a 2 by 1 matrix. Right? That's why you're learning matrix, because when you do vector addition, it's matrix addition. Yeah, it's like, okay, maybe I'll tell you a little bit in advance since we've got so much time. If you have a vector 2, 4, which is that arrow there, and then you plus another vector 1, 0, what does that represent? Well, if you do matrix addition, let's see, that would be 3, 4, right? Okay, but what does that mean actually? So 1, 0 represent the vectors that is 1 to in the x direction and 0 in the y direction, right? So it's just be that tiny vector here, right? From 0 and it goes to 1 like that, right? Now, when you're doing vector addition, what you're actually doing is you're connecting the vectors. Yeah, so it goes from the start, it goes 2, 4, right? It goes 2, 4, which becomes that the one there, and then it goes 1 to the x and then 0 y, right? Which means, give me a second, I'll come out. Which means that this one goes to 3, 4. So it goes 3 to the right and then 4 up.
Oh,
does that make sense?
Yeah.
Yeah, so this is actually what vector or what matrix addition will be used, and that's the meaning of vector addition. Give me a second. Okay. Yeah, it's just true. Yeah, you just came back. All right. So yeah, so that's actually that's the meaning of that's one of the applications of matrices. Okay, when you do vector addition.
If you like plus the 1 and 0 first and then do the 2, 4, will it still be at the same position?
Yeah, it will be the same position. Let me borrow a grid online. I'll show you. And yes, you are talking about. Okay. And you're talking about the commutative property of matrix addition. Okay, very good thinking. Let's see. So first, if you go, so remember that we're doing 2, 4 and then plus 1, 0, right?
Yeah.
As opposed to, we do the opposite, 1, 0 plus 2, 4. Now, mathematically, remember how I told you the rule earlier, these two must be the same, right? Because when you add 2 and 1, it's just 3, 4, and the bottom is also 3, 4. Alright, so this one is the same mathematically. Let's see if it's representing the same thing. 2, 4 means go 2 here, 4 here. So the first vector is this one. Right? And then 1, 0 is from 0, you go just the 1 here. Right? So again, connect the vector. If you connect, if you connect just this vector here, it goes to 3, 3, 4, right? But if I have this one here, and then I move this one, connect it afterwards, it is still the same. It still go to 3 to the right and then 4 up. So it has commutative property, right? Yeah, because you're just adding the component. So in total, you're just saying that, okay, you move 2 and then 1, and then you move 1 and then 2, same thing, right? And vertically, you move 4 up and then 0, or you don't move, but then you move 4 up. It's the same thing as well. It's ultimately, it's just moving 4 up. Yeah. So that's the visualization of, I guess, vector additions. I don't think you're learning this term, the vector stuff. You're just learning matrices, I think. Pretty sure. Let me double check your plan again. But yeah, so your week, this one is just about multiplying matrices. So yeah, skip. We did that already. Looks scary, but it's just this is what I showed you earlier. Okay. I don't like seeing these things because it's harder to deduce all of this than just, it's harder to deduce all of this one rather than just to show you that it's just that one times that one, get the first number, and then times by this, get the second one, and times by this, get the third one. Right? That's for the first row. Okay? And then you take the second row, times by that, get the first number, times by this, get the second number, times by that, get the third number. Okay? So the answer will just be another 3 by 3 when you do the last one, times this, and then times that, and then times this. You can try. On paper, try this one. Find A times B.
A times B?
Mm-hmm. Oof, you're learning permutations and combinations. That's the one that most people get very, very confused about. It's going to be interesting. Okay.
What do you do for the second row? Do you just keep writing?
No, let's see. So that times that. The second row will be the second row.
What about this one?
Let's see. So you do 2 times 4. You're supposed to add them together. So 8 plus 3 plus 0. That's one number.
Oh, that's one number?
Yes, that's one number only.
Mm. Look at this.
11, 18, 14, should be 26.
Oh, it's 1.
Yeah, so sometimes it's a bit tricky to do this multiplication, right?
Yeah.
But once you get the algorithm, it's actually not hard, right? So yeah, that should be it. Like these ones, yeah, I think when you get to the school, you can practice these ones. What product doesn't exist is what I said earlier, where the 2 dimensions closest to each other must match. Yeah, when you're trying to find which one does not exist here. Yeah, no, should be okay. Yeah, that's it. That's lesson 1 for multiplying matrices.
What is lesson 2?
Identity and powers of matrices. Okay, lesson 2 for week 4 is getting a little bit harder. Not too hard though. I think you can still get it. Let me show you. So know that this is week 4 content. You will only learn this in 2 weeks time. So you should go back and practice. Yeah. Do you have a textbook for this? Or just these notes?
Just use PowerPoint.
Oh, okay. So that means your school is trying to prepare you for specialists, so they're making like special content. That's fine.
But I think we have a textbook though. I'm not sure whether it's for methods or specialists.
Method and specialists both have textbooks.
It's Jacaranda Plus, I think.
Jacaranda, right? I have the Cambridge one, not the Jacaranda one.
Which one's harder?
I haven't seen the Jacaranda one yet, but so far the Cambridge one is pretty decent. It has some really difficult questions. I don't know about the Jacaranda one. So, well, maybe since you're probably going to be ahead of the content, I'll give you the Cambridge one. I'll just give you the PDF version, so you don't need to buy it. I'll give you the PDF version. You can start practicing.
How big is it?
Like the PDF?
Yeah.
Like 50 megabytes. I can just give you a link.
Huh.
Yeah. I'll just give you a link on Google Drive. You can go on and download it and just access it digitally. Really easy. I don't tell anyone I do that though. Just be like, oh, I found it online. Okay? Because legally, I'm not allowed to distribute like copies of textbooks to students without. So normally you have to pay for the textbook and then be able to use it. But it's fine. Nobody checks these things anyway. As long as you don't be like, oh, hey, I got this one free from Koi and start giving it to everyone. And they will chase it back to me and I'm in trouble. Okay, so yeah, let me start. Let us go through the identity stuff. Identity matrix and the power matrix and powers of matrices. It's not hard, but could be a bit more tricky. Okay, I'll just go through the main content and I'll give you some examples. So powers of a matrix is like when you multiply a matrix by itself. Alright, so a squared, which is be a times a. Alright, and then a cubed is a squared times a. Now, the important thing is when you multiply together, you need to multiply in this exact order. You always need to do left to right. Okay? Okay, what that means is, for example, let's say you do 3 cubed, right? It's like 3 times 3 times 3. So in normal algebra, you can do these two first, which is 9, and then that will be 27. Or you can do these two first, and it's still the same. Right? In matrix, it's not the same. Okay? So in matrix, the order is really important, and you always do left to right. So let me show you what I mean. And only square matrices. So what is a square matrix? Right? So this is Wk4 lesson 2. Square matrix. A square matrix is an n by n matrix. Basically, same row, same column, like a 2 by 2, right? Or like a 3 by 3. Okay, very common. That's why they have a special name, because it's so common. So let's say the 2 by 2 matrix. So let's say if we have a 2 by 2 matrix, I'll use the simple one, 1, 2, 2, 1. Okay, let's say this is A. Right, the matrix A, we call that 1, 2, 2, 1. If you want to do A squared, is the same as 1, 2, 2, 1 times by 1, 2, 2, 1. Right? Again, first row, first column, that would be 1 plus 4, that would be 5. And then that would be 2 plus 2, which is 4. And then 2 plus 2, which is 4. 4 plus 1, which is 5. It would be like that.
So when I calculate, it's just so messy.
Yeah, when you get used to it, it will be a bit faster. Like when I see it, I'll see this one and that one. I just times the top two numbers, so that'll be 1, and then I just remember plus 2, 1 plus 4. Right? So because I know it's just plussing together, so I just get the product. Normally is easy, and then just add them. Yeah. So 5, 4, 4, 5. Now, when you want to do a cube though, you need to take this value and times by another a. So it'll be this one, 5, 4, 4, 5, and then you times by 1, 2, 2, 1. Okay, and same thing. 5, 1 is 5, 4, 2, 8, so 5 plus 8, or if you want, you can just write 5 plus 8 here. That's okay. And then you go 10 plus 4, right? And then that will be 4 plus 10, and that will be 8 plus 5, for example. Right? That's okay. If you do it in 2 steps, that's fine. Not a big deal. Okay, but if you can do it in 1 step, it will be faster, of course. But sometimes when the number is too big, it's safer to do it in multiple steps. So 14, 13.
But if you do the last two first, wouldn't the answer be the same?
Maybe I actually use one of the special matrix. Let's see. So if I were to swap that around, 1, 2, 2, 1, and then 5, 4, 4, 5. Okay, so instead of doing a squared times a, I'm going to do a times a squared. Right? So that would be 5. Yeah, 5 plus 8, and that will be 4 plus 10. Okay, I think I accidentally used a special special matrix. Yeah, my bad. I used a special one, so that's why I can't illustrate the point for you because these two are the same. All right, my bad. I will try it to change it to 1, 2, 3, 4. So the number is going to be a little bit harder to calculate, but I think it will make the point clearer. 1, 2, 3, 4. All right, let's quickly work this one out. So 1 plus 6, 7. 2 plus 8, 10. 3 plus 12, 15. 6 plus 16, 22. Okay, and now if we were to do a squared times by a, which is 7, 10, 15, 22, and then times by a, which is 1, 2, 3, 4. Okay, all right, now let's see. All right, let's quickly get the answer. So I'll do a times by a squared. All right, just to see what the difference is. So that'll be 7 plus 30, 37. 14, 40, 54. 15, 66, 7, 15, 66 is 81, and then 30, 88 is 30, 88 is 118. Right? I'm just going to copy this, paste that one here, then change it up, paste that one here. Okay. Yeah. Oh wait. 10. Wait, is that the same? It is the same. Wait, it is the same. Hang on. I think I'm confusing myself a little bit. Hang on. I think matrix has, if it's the same matrix, it has, square matrix has commutative property. It's the other matrix that you can't flip that around. Hang on. It's the same matrix. Yeah, you're supposed to, it's not supposed to be the same, but sorry, need to go and double check my facts. Normally I don't do this kind of matrix proof that often, but because okay, let me tell you my reasoning before. So remember how we had like a 1 by 3 matrix, and then when you times it by like a 3 by 2 matrix, right? The answer is a 1 by 2 matrix.
Is it always the two like outer number?
Yeah, good guess. Because 1 by 3 is like if you have let's say one row A, B, C times by 3 by 2, which would be your 3 rows and then 2 columns. That'll be, let's say, all ones, for example, right? So when you times it all together, let's say it's all 2's here. So when you times it together, it would be 2 to 2, so it would be 6. And then 2 to 2 would be 6. So that's a 1 row and 2 columns. So yes, you're correct. It would be this one and then that one. Right? It would join together. Okay, so the dimension will merge that way. But if you were to flip that around, 3 by 2, and then times it by 1 by 3, you can't, because the two closest ones they're not the same. So you can't flip the multiplication of a matrix if the dimensions are different. So 1 by 3, that one would be saying 3 by 2 is the 1, 1, 1, 1, 1, 1, and then you're trying to multiply that with 2, 2, 2. So if you're trying to get the row here with the first column, you can't, because the numbers don't match up. Okay, so in general, A times by B is normally not the same as B times by A. Like one way may work, but the other way may not even work.
Oh, so if you flip it around, then it works because it's all 3.
Sorry?
If you like put the 1 times 3 in the front and then the other one at the back, the middle one would be the same, so it works. Is that what it's trying to say?
You mean for this one here?
No, for like that one, that example.
For that example there?
Yeah.
Yeah. Yeah, so if you flip that around, then it will work, yeah, because the 2 3s are in the middle.
Is that what it's trying to say, or?
Kind of. But yeah, let me double check. Square matrix. Let me fact check this. I haven't checked.
I think I'll just square the first two anyways.
Yeah, just would be kind of. I think it. Yeah, matrix model is not commutative. So when is it? Oh, this is I think I used some special ones. I think I just made up. So my matrix is a little bit special, so it's commutative. But normally it shouldn't be commutative. But yeah, normally you just go left to right. Yeah, just remember, just go left to right. When you do matrix multiplication, that's the easiest one. Okay, so I think we've covered up to week 3 lesson. Yeah, so I've covered square matrix, but yeah, that's not yet week 4 lesson 2. So week 4 lesson 2 is the identity matrix and the powers of matrix. Oh yeah, I covered half of that. Yeah, so it's just the identity matrix left. Maybe I'll just mention it briefly. It's not too hard. So the identity matrix, right, that's the powers of a matrix. Oh wait, what? Is that it? Oh yeah, here. So the identity matrix is a matrix where the leading diagonal is all ones and the rest is zeros. Why? Why would that be called the identity matrix? Well, let's say this matrix is a 5 by 5, right? And if I want to multiply that with the 5 by 1, let's say 1, 2, 3, 4, 5. The answer will be the exact same. Why? Well, let's see. First row, first column. There's only one column, so the answer will be one column, right? But let's say first row with the first column, you see the only number that is retained is the first number, right? And that becomes the number 1 here. And then when you move it to the second row with the column, which number is retained? The second number, aka the number 2 is retained, right? And if you keep on repeating that, right, if you keep on going down, the third row, the only number that's retained is the number 1 here, because when you multiply, the rest will become 0. So the number 3 is retained, right? And that's why you need the 1 in the leading diagonal, because you're shifting which number you want to retain when you multiply, because when you multiply, it's always like a horizontal times a vertical, right? And the fourth row just means, okay, ignore everyone but the fourth number. And then the fifth row, when you times in, ignore everything but the last number. That make sense? Yeah. So that's why the identity matrix is just the matrix is a it can only be defined for square matrices, technically. Yeah, because the identity matrix is one where when you multiply it in either way, the answer will be the same. Now this one is not a square matrix, so when I take this and chuck that to the other side, it doesn't work because the dimension don't match up, right? So technically, the multiplicative in identity matrix only works if this rule here only works for square matrices. Yeah, I'll just give you a very quick example. So it only works for square matrices, so 1, 2, 3, 4. If you times this one, the answer will be the same, right? Or if you times in this order, the answer will also be the same. Well, either way, it will be the same. Okay. What else? What else do you need to cover? So the identity matrix. Oh yeah. So okay, do you have any question about the point that if you have even two square matrix, let's say 1, 2, 3, 4, and then you times by, let's say 1, 0, negative 1, 2, this is going to be not the same as when you flip the 2 around, like 1, 0, negative 1, 2, and then 1, 2, 3, 4. Okay, any question on this? It's not the same. You can test it. That times that is 1 times 1, which is 1. 2 times -1 is -2. 1 minus 2 is -1, right? So that will be -1 something something something. But the first answer is -1. If you were to work this one out, that and that, 1 times 1 is 1. 0 times 3 is 0. So the answer here is 1. It's already different.
Why?
Why? Because you see how, okay, I'll draw it out. If you, this one here is the red dimension, the red numbers that are multiplied together, right? On the left hand side, like the first matrix is the horizontal one. But if you swap them around, the red is horizontal, but you actually multiply the vertical numbers if you swap them around. Because then you take the first matrix, you would take the horizontal instead of the vertical. Does it make sense? Like this one red goes here.
Oh.
Yeah, so that's why the numbers will be different. So it's not commutative, right? When you multiply two matrices, if you swap the position around for square matrix, you can still multiply them, but the answer is not the same.
Oh, but didn't like the problem say I times A equals A times I or something like that?
Yes, because this is a special one. This is the identity matrix I. This is the same because
the 1 and 1.
Yeah, so 1 0. 1 0 means you keep the first number, and then if you times this one here, it will be exactly the same. So that's why it's special. Right?
Oh, yeah.
This is the only one that works.
Oh, because it's always 1 at the first one, and the second row and second column, they're all the same.
Yeah, that's right. Okay? Yeah, that's it. Identity matrix. Done. Make sense? Yeah, what do you think about matrices?
It's interesting.
Interesting, right? Should go back and practice the algebra. You can practice up to lesson 2, week 4. Okay, this one I would go week 4, lesson 1 and 2. Alright, I'll upload the notes and the recordings later.
Yeah.